Hello everybody and welcome to the NPTEL online certification course on CMOS digital VLSI design. We start with the second module of memory and its design, and in the first module we have seen the basic architecture of a memory and what is the basic parameters. For example, how do you define read access time and write access time. We have also seen how does what are the various peripherals which are generally there. And let me therefore come to this module and explain to you, as I was discussing earlier, that we will always keep generally the height is much larger than the width. So, you try to keep the height larger than the width, so that your address decoders are relatively easy to handle the bit of data. The column decoders are meant for selecting appropriate words, as I discussed with you, and row decoders are selection of the bit line and bit line bar. Let me come to the hierarchical memory architecture, therefore, which means that if I have a memory generally, then this is how it looks like. So, this is the block, so this is the block 1, block 0 which you see, or block 1, these are the memory blocks which is available to you, right, and you have a row address which is this one, which gets access through a row decoder across the whole blocks of memory. You will have also column decoders or column address decoders, this and this, and they will be actually responsible for selecting the appropriate bit or bar line. This will be finally given by the block address decoders here, right, and therefore, there will be a global data bus which is fed here. So, our data can be written or read from this global data bus. You will have a global amplifier or a driver which is responsible for amplifying the signal, and then finally, it will be connected to the final I/O. So, this is from where you will get inputs available to you. This will amplify your signal, send it to a global data bus. If you want to write the data, say in the say ith block, then you can actually select that particular block using the block address, and then use the column address to select the particular bit line and bit bar line, and similarly the row address of the word challenge, and then you can actually store a bit of data at that particular point. You also have a control circuitry here which controls the flow of the signal between the I/O pads and the block level diagram. Now, the idea behind this is that the global data bus which you see is, if you look very closely, is effectively isolated from the memory block, because you do have a block address and a column address decoders which help you to decode the address. Now, generally there is a problem that you require that your noise margins of memory should be high, and the reason is that since this global data bus is connected to I/O, which is external data, therefore, this global data bus is prone to large amount of noise, right. So, these noise origin might be right from a VDD difference, a change in the power line noise, or it might be even a 1/f noise, it might be even a process noise, so on and so forth. As a result, what will happen is that at certain point of time, if your block address and the column address are both in the on state, your ith block will be connected to the global data bus, and therefore, even a small finite change in the noise margins or a small change or a small input of the noise in the global data bus will actually change the noise margin, or will insert noise into the system, and a 1 might be actually read as a 0 or vice versa, right. So, we have seen in our previous discussion that there are two noise margins, which is high noise margin and low noise margin, and depending on whether you are storing a bit 1 or 0 or reading 1 and 0 from the point, you should be very careful about that. For example, if you are reading 1 or you are reading 0 and then suddenly there is a noise inserted into the system, that 0 might be even read as 1 provided the noise voltage is approximately VDD by 2. So, you should be very careful about these noise getting separated out at the very initial stages, and people use this hierarchical architecture to do that. Okay, let us look at the memory core now. We will not be looking at the peripherals at this stage maybe, but we will be looking at the memory core where one bit of information will be stored here. The general memory core, though not shown here, I will just show it to you, is basically made up of sorry, I will just make it for you. So, it is made up of a large number of word lines. So, these are your word lines WL1, WL2, and then you have, this is in a shared bit line architecture. So, you will have such sharing. So, say this is bit line bar, then you have bit line bar, bit line and bit line bar. So, if you have one stored, if you have one coming here, a 0 1 coming here, a 0 will be coming here, and so on and so forth, and these are the memory core cell. So, this is cell 1, cell 2, cell 3, cell 4, cell 5, and so on and so forth. Now, if you want to access, for example, cell 3, then you keep your word line WL1 high, and therefore, this will be all high. I will show it to you in the later slides, and then you make a bit and bit bar line work for you. Then this cell will be selected, right. So, this bit and bit bar line, this need to be selected, and then you can select this 3. Similarly, if you want to select 5 number cell, then you select WL1 and then select this 2 bit line. Similarly, if you want to select this line, right, then select WL4 and select this bit line and bit line bar, right. So, this is basically a array of columns and rows, and by selecting appropriate columns and rows, you will be able to select a particular cell for writing or reading purposes. Now, if you look, so let us now compare that same architecture with what you are seeing in front of you. Now, let us suppose you have diode here, a word line and a bit line are connected. Suppose your word line is 1, right, then this diode will be on, and this 1 will be written onto a bit line here. So, that is the most simplest method of writing, but this is basically a ROM, which means that once a 1 has been written, you cannot rewrite it over and over again. Once it is done, it is done. So, once you have a diode connection between this WL and bit line, which is shown here, you generally do not have anything else to. So, and if there is no connection between these two, 0 will be stored, right. Similarly, if you have word line, so similarly this is basically a diode based, you can also have a MOS based. So, this is basically diode based ROM, you can have also have a MOS based ROM, where you have a MOSFET which is kept here, right. And so, when your word line becomes high, this MOSFET becomes on, and when it becomes on, this VDD is connected to this point, and therefore, bit line goes to VDD, right, it goes high, and it goes to a higher value available to you. If there is no MOSFET available to you, then we say 0 to be the obvious thing. Another way of looking at it is that if you have word line high, then bit line will be writing 0, because this is grounded here, and if we do not write anything here, you will have 1, in this case 1 it will be there. So, there are 3 major compositions of read only memory. One is basically a diode ROM, right, another is basically a MOS ROM 1, and the third one is basically MOS ROM 2. In the second case, which is MOS ROM 1, depending on the on state or off state of the MOSFET, your output bit line will be either charged to VDD or to ground, or generally to VDD for storing 1, and if there is no MOSFET in between, it will be storing 0 there, whereas the reverse will be true in case of MOSFET 2, wherein if you have word line high, bit line will be storing ground 0, and in the other case it will be storing 1. So, these are the basic memory core which you see as far as ROM is concerned. Let us look at a 4 by 4 OR based ROM array, right. It is pretty simple and easy to understand. Say for example, your WL1 is high, right, it is 1. So, this switches on this data, this switches on this one, and therefore, this VDD is written here. So, this is equals to VDD, right, this is equals to VDD. Similarly, if your WL0 is 1 and this is also 1, then your VDD is again written here and a VDD is again written here, and therefore, there will be a VDD available at this particular point, and so on and so forth, right. So, these are basically, these are which you see here, these are known as pull down loads, these are known as pull down loads. Why they are pull down loads? Because they are responsible for pulling down the voltages to ground once the data has actually been written there, right. And this is basically a ROM array, 4 cross 4, because it's 4 cross 4, because it is, there are 4 word lines 0, 1, 2, 3, and there are 4 bit lines 0, 1, 2, 3. And depending on that this thing, the V bias which you see here will be responsible for, so they will, these transistors here will act as a resistive transistors. So, they will act as resistances, and therefore, when your B bias goes high, right, these get switched on, and therefore, they act as pull down resistances for all practical purposes. This is 4 by 4, and therefore, bit line will be equals to 1, bit line 1 will be again equals to 1, bit line 2 is nothing is there. So, it will be 0, and bit line 3 will have again 1 available to you, right, and this is how a 4 cross 4 OR based ROM will be there. I will not go into details of how it works out, because that is quite a subject by itself, but if you look at non-volatile read write memory, these are the few examples here. The left one is basically a floating gate transistor, then you have an EEPROM, which is erasable programmable read only memory, and then you have flash EEPROM available to you, right. So, these are the 3 types of non-volatile read write memory which is available to you, and depending on the distance between the floating gate and the original gate, you can actually lower or higher the data, and therefore, in this you can actually store a data. In this case, once you actually remove the power supply, all the charges are removed, and therefore, you do not have any data being stored during the VDD equals to 0 case. Let me come to a static 6, this is basically known as a 6 transistor SRAM cell, right, and this 6 transistor SRAM cell actually stores 1 bit of data. So, this is known as 60. Why 60? Because 1, so M1, M2, M3 and M4, M5, M6. If you look very carefully, this M1, M2, M3, M4, they form a back to back connected inverter, and then you have an access transistor which is available here. So, this is the word line which you see in front of you, this is the word line, and this is the bit line which you see, and this is the bit line. So, M5 and M6, M5 and M6 are referred to as access transistors, right. They are referred to as access transistors, and M1, M2, M3 and M4 are part of the CMOS inverter pair which you see. So, if you make your word line high, both M5 and M6 switches on, right, and therefore, your internal cell, which is the internal value of Q and Q bar, can be written on bit and bit line bar respectively. So, by simply choosing which word line you want to make high, you can make all the cells high, and then depending upon which one of the cells you want to choose, you can take typical values of bit or bit line bar. This is also known as a static random access memory or SRAM, and it is known as 6T SRAM cell, right. Before we move forward, I need to explain to you just 2 things, and these are, so I have got a inverter, right, and I have got an inverter here. So, this by itself, as you can understand, is a memory. So, this by itself is a memory. What does it do is something like this, that I have a memory here, and then I have cell here, cell here. So, whatever, suppose I am storing 1 here, this will be 0. So, this 0 will go again here as a 1, and therefore, this is a closed loop available to you, and therefore, when your word line goes low, suppose it is 0, then this is also 0, 0, then this cell is totally insulated from the external peripherals, and therefore, you can store the information for a large period of time. Please understand, this is basically a very high impedance node, right. This is typically a high, this node and this node is Zin is very almost infinity, Zin is infinitely high. It is very high impedance node, as I discussed with you earlier, because CMOS input side will be the gate side, and as a result the charge storage is very proper, and there is no leakage available to you. You can store a charge for a longer duration of time. But the problem here is when you make word line high, right, and you make word line high here, then this cell becomes transparent, and that time you can read or write the cell. We define 2 important terms here. One is known as the pull up ratio and one is known as the cell ratio, right. Pull up ratio is the ratio of the W by L of access to W by L of pull up, which is PMOS, right, and cell ratio is W by L of access to W by L of pull down, which is NMOS. So, we define cell ratio as this one, and we define PR to be equals to this much. So, we have a cell ratio and we have a pull up ratio, and these two are quite important in understanding the whole issue of working principles. Let me come to SRAM read and write operation. So, read operation is very simple and straightforward. So, you see you make your word line high, this becomes on, right, and this also becomes on. Say you were storing a bit 1 here and therefore bit 0, then you please understand M4 will be on because you are grounding M4, and as a result when this becomes on, this VDD is connected to this much and this 1 appears at the bit line bar here. Since this is on, this is VDD, this is also on, therefore, you have a pull down load available to ground and therefore, Q bar equals to 0. So, Q bar appears at bit line bar. This is a very simple straightforward way of looking at it. When you want to read a cell, therefore, it is quite easy that out of M1, M2, M3 and M4, M1 and M4 are switched on, right, and M4's gate terminal is always grounded. In this case, it is grounded because your Q is equals to 1 and Q bar equals to 0. Since your Q bar equals to 0, M4 gate will always be grounded. I think I have made it myself clear. See, M4 is connected to Q bar, getting my point. So, when this Q bar equals to 0, M4 is on, and when your Q bar equals to 0, M3 is cut off, right, because it is an NMOS. So, it will not be switched on. Similarly, M1 will be switched on because why it will be switched on, because Q equals to 1, let us suppose, then M1 will be switched on, and so it will pull this voltage to ground and therefore, Q bar will be equals to 0. So, exactly the same concept applies here, that this will go to 0 and this Q bar will go to 0 and Q will be equals to 1. This is for the read operation. If I want to go for write operation, then the simple, it is simple as well. Simple, when you want to write it, say Q equals to 1 you want to write, then you want to make bit line equals to 0 and bit line bar equals to 1. So, what it will do, this will override this 0 to 1 and this will override 1 to 0, and then you can go for write operation. So, write operation is when this is connected to VDD and read operation is when you connect it to directly to the ground here. There is another technique, static random access memory is static. Why? Because you do not have to refresh it. Once you have stored a data, it remains there for a long duration of time. However, there is another type of RAM which is known as dynamic RAM or DRAMs. This cell is basically 1T 1C cell, one transistor, one capacitor. So, M1 is basically the transistor which you see in front of you, and CS is basically the capacitor across which you are storing the data. So, whenever your bit line 1 is high and your WWL is high, so whenever your WWL is high, this is high, right, your X value starts to rise, right, X value will go on rising. Why? Because when this is high, M1 is on, bit line is suppose is 1. So, when bit line is 1, X will start to rise, right, and so you see this rising of X, but it rises after some time. This is because of the delay which you see in front of you. Then X as rises, so it stores data at CS, right, it stores data at CS and it goes to a high value approximately equals to VDD. Now, as it goes to high value, M2 switches on, and when M2 switches on, this gives a low conducting path for M3, and therefore, initially when this is 1, this was 0, this was 0, then this will actually go to 0 ground, it will ground it when you make your RWL high. So, when you make WWL your high, means write high, then you actually are able to store a 1 from bit line 1 onto X node by this thing, and when you want to make the bit line too high, when you want to make it bit line too low, then you actually ground it across M3 and M2. So, this is how you actually see basic dynamic RAM, but the problem here is, since the capacitance itself, which is the voltage across the capacitance, will actually be leaking because the capacitor leaks, you need to refresh this time and again for the dynamic RAM, right. So, let me recapitulate what we have done in these two modules of memory. We have not gone from peripherals, but we have just given a brief idea about the memory core. We have also looked into the various applications and the system requirement. We have also looked into EPROMs and E2PROMs, and then we looked into the various elements of static random access memory and dynamic random access memory. We defined what is cell ratio, what is pull up ratio, and we have also seen how can you read and write in a cell in a memory, right. So, this comes to an end for the memory design. We will take up in the next time. Thank you very much.